Good morning, I am Krishna Kumar. Well, it's after a long time we are back on this topic. Precisely, I think I did my last lecture on this topic sometime during the last week of December. And since then I had been busy recording talks on linear algebra and concentrating more on that at that time, because I was also simultaneously teaching the same course at the Kerala School of Mathematics. So I thought that it is time I picked the threads back and continued with this set of lectures. Now, where we stopped last time was with the definition of derivative, or what you call the total derivative, or what you call the Frechet derivative, and considering some, in the last lecture we considered exclusively spent time on working out some examples, and which gave a lot of insight into how things do not work as we expect when we deal with the functions of several variables. Gives a lot of insight into the problems that you have to look for. So anyway, let us begin or resume this series by recalling the definition of a derivative. So let us put it on the board. Let E be an open subset of Rn. Now let F be a map from E to Rn. That means a vector valued function. Both Rn and Rm are normed linear spaces, and let X belong to E. If there exists a linear transmission A belonging to L that means a linear transformation from Rn to Rm such that limit h tending to 0 of norm of zero. Well, I think some caution is we should have here is that the norm that you describe on the top and the norm that you describe or you use in the denominator are different, because you know that fx plus h and fx are vectors in Rn, and therefore the norm that you are using here is the norm of Rn. So if you want, I don't want to write this every time, but at least here let me write Rn. And in the denominator what you have is the norm on Rn, but I will be dropping this subscript with the norm, and one has to really understand what exactly what norm we are using there. Okay, so we'll keep this. Let if there exists A belonging to Lr and Rm, that is a linear transformation from Rn to Rm such that limit h tending to 0 of this. Of course, here h belongs to Rn. h naught equal to 0. And h tends to 0 means norm of h goes to 0, that is the equivalent form of it. Then we say that f is differentiable at x, and we write the derivative f x, that is now we also note that if f is differentiable at every point of then we say that f is differentiable on E. Now, a few things that you should realize is that this A essentially changes from point to point. Okay. This is in fact a linear transformation which varies with x. That what I mean to say is that if you take 2 points x1 and x2, the linear transformation that you get are different, are not necessarily the same. Okay. So that is something that you have to note. Okay, this is a local derivative that you have actually essentially computed. Now this we have done, if you just recall, this we have done by first recasting our conventional notion of a derivative for a real valued function of a single variable in this new language. Okay. And then see, there was no need to go to this particular language there, because division by h was possible at that time, because the increment that you take is a real number there. Therefore, you could have talked about f of x plus h. If you recall our definition of the derivative of a function of a single variable is that f of x plus h minus f of x divided by h, limit as h tends to 0. And that is perfectly sensible, because what we had in the denominator was a real number. Whereas if you work in Rn, then you see that you cannot divide by a vector. So you are taking a vector in Rm and dividing it by possibly by a vector in Rn is not possible. Okay. So you have to recast the whole thing. And we also observe that in the one-dimensional case, the derivative, the conventional notion of derivative is that it's a number. Okay, depending on the point. Okay. Now, what we observe is that if you take a one-dimensional vector space, then every number manifests as a linear transformation on that. Okay. Therefore, it gets a new image altogether. Conversely, if you have a linear transformation on the one-dimensional vector space, then you see that it can be represented by a scalar. So this identification is there. So it is that aspect where we concentrate, and then when you generalize the whole idea of functions from Rn to Rm, what we are looking at is the nature that f derivative of x is looked upon as a linear transformation from Rn to Rm. This is the generalization. That's how we have arrived at this particular notion. So we recognize that the derivative is essentially a linear transformation from Rn to Rm. This is a very important thing. Now we make some remarks here, just recalling, then we go to the change. So remarks, worthwhile to note it. If f is differentiable, then the derivative is unique. Or rather, we will say that only if it is unique, there is some sense in calling it the derivative. In short, what we say is that the A, oh sorry, I think I made a mistake here. Okay. There's something missing here. I am sorry. I think I should correct that. You have is that. Sorry, it's a very grave mistakes. Sorry for that mistake. I'm sorry for that mistake. This is what it is. Okay, right. Yeah. Yes. Okay, that's fine. Right. Okay, that's clear. So the derivative is unique. That is, A that you have is uniquely determined if the limit exists. Okay? If A1 and A2 are two such linear transformations for which this is true, then A1 is equal to A2. That's the first one, first remark. The second remark is this, that equivalent form of just note this by designating this star is the following. It is f of rather I can write this as, if the derivative exists, this is f derivative of x, h operating over h plus, that is the error term that you have, and the error term has the property now you see that this is in Rm, this is also in Rm, because you see that H belongs to Rn, f derivative belongs to f derivative at x belongs to Rn to Rm, which implies f derivative of x acting over h. So this is in Rn, Rh is also in Rn. This is the error term that you have. Okay, when you take the difference of f of x plus h minus f of x and approximate it by ah, or just filter out the linear part from it, then the error that you make is denoted by RH, and RH has the property that RH divided by norm of h goes to 0 as h tends to 0. Also RH belongs to R. Okay, so this is actually Rm by Rn by Rn. So this is again Rm divided by Rm divided by, this is what you have. Okay. Secondly, third remark is that if the derivative now a specific example situation is that if so these are little things that we have probably mentioned earlier. Now henceforth I will not be writing Rn and Rm following this norm symbol, and they take the appropriate meaning whatever is sensible in Rm or Rn or where the vector is and so on. So I will use the universal notation norm. So that norm is the relevant norm. That is what I mean. Okay. So let me now go to what is called the introducer chain rule, which we are familiar with. Okay, let us just recall what it is in the one-dimensional case. Suppose f is a map from some interval I of R to R, the real valued function, we assume it is differentiable at some x naught belonging to I, and assume G is a map from some open set, some J open in R to R, and we take this G to be differentiable at f of x naught. So you see that there is a composition of these two functions define a function from I to R. So the question that you have asked, or you already know, is that what is the derivative of this composition of this f and g? Okay. So that's the question that we are asking, and we know that the chain rule just gives the answer to it. You see that. So okay, so if now assume, what we assume is that G is differentiable at f of x naught, f is differentiable at x naught, G is differentiable at f of x naught. If so, we conclude that capital F is differentiable at x naught. Differentiable at f of x naught, then capital F is differentiable as a function from Rm as a function from E to R at x naught, and the derivative is given by in terms of the derivative of G and F. What you obtain is the F derivative G derivative at into these are of course numbers, so you get this is a number, this is also a number, therefore product is there. Now the only problem that you have is that when you are generalizing it, the same result holds, but then you have to be careful about the order in which you write them, because here everything commutes, so there is no problem whether you write f dash x naught into g derivative of f x naught. So they are the same because they commute. But this, you cannot write in the general case. One has to be careful about, because we are talking about mappings from Rm to Rn or Rn to Rn. Okay, so let us write down what is feasible, the chain rule for this. Okay, make a statement. So we write down the following theorem. I use the same sort of notation so that you can follow it. Let be differentiable at P. E. Let G be a map from an open set containing what is that, f of E into Rk, where k is some positive integer, and assume G be differentiable at f of x. Then the function f capital F from E to Rk defined by f of x naught equal to, what is it, equal to g of f of x. Hey, that is, you write it as g composition. This is the definition for x belonging to E. Is differentiable at x naught belonging to E and capital F derivative at x naught is given by G derivative at Now, before we prove this theorem, we will make some remark. Now, you see that F is a map from Rn or E contained in Rk by definition. Therefore, if at all F is differentiable, F derivative at x naught belongs to is a linear transformation from Rn to R. Now you see that F derivative at x naught is a linear transformation from Rn and G derivative at f of x naught is a linear transformation from Rm to Rk. Therefore, and suppose I denote this by A and denote this by B, then what you have? Then what I get is that f derivative, this is equal to BA, and it is in that particular order and you cannot change the order, okay, because A and B need not be commutative. When we were working on the real line, that is from R1 to R1, we were talking about real valued functions defined on subsets of R. This problem was not there because both B and A were scalars and they always commuted. Okay, so we could have written it in any order. So that is something that we have to, so the order is important. Cannot change it as you like. So this is the chain rule that we have. So it's exactly as what we did in the one-dimensional case, but now you are working with operators. Okay, and you can easily see that if you have a map from, see, G dash acts, sorry, F dash acts from Rn to Rn. Okay. So you have reached Rm and from there you are working with G dash and G dash is from Rm to Rk. Therefore, you are carried from Rn to Rk. So that everything checks well, but we have to actually see that they are, the right hand side is equal to the left hand side. Okay, so let us start more systematically. Okay, so let me have some pictures here or some what you call figures to explain out things. This is E is an open set and x naught is some point here. And then you have the next space. So this is Rn, this is Rm. In Rm you have got Fe. This is your Fe. and this is inside some open set where G is defined, and then you have from here G is from here to R. So what you have is this: x naught is mapped to f of x naught. This is by f, and then G maps it to this one, and this is what you call, this is f of x naught. Now we are talking about the derivative of capital F at the point x naught. Now what we want to prove is that this result holds. So we introduce some notations. So let us define y naught, this is for convenience, and a you write as f dash, f derivative at x naught, b you write as g derivative at f of y naught is f of x naught. Okay. Now we use the fact that f is differentiable and g is differentiable. F is differentiable at x naught, g is differentiable at y naught. So we will make use of that. So define, we use this notation. This is the error term. UH you define as the error when you replace it by AH. F of x naught plus h minus f of x naught minus AH for every h belonging to Rn such that, okay, we will write h belongs to Rn and a plus what is that, x naught plus h belongs to so that f is also defined there. Okay. And similarly, we have a estimate of the error that you have a notation to depict the error that you have if you replace by f of y naught plus k or g of y naught plus k minus g of k. So let this k is not the same k that you use here. Okay, this is a positive number, whereas k is a vector. Okay, so this is equal to g at, let me write this, k minus where of course k is a vector in Rm, okay, where k belongs to Rm. Is a vector in Rm such that okay. So then what you have is that f is differentiable at x0, g is differentiable at y0. Y0 is equal to f of x0. So these two conditions we write. Since and g is differentiable at y0, what we have is this norm of UH, that is the error term. This is UH is in Rm, and with epsilon h going to 0, so epsilon h goes to 0 vector as h tends to 0. This is the error term. Okay. Now this is certainly in what you call UH is where okay, this becomes an similarly you have norm of Vk. This is equal to eta k. This is a number, norm of k, and eta k goes to 0 as the vector k goes to 0. This is the relation that you have. Or I think we have expressed it by saying that UH divided by norm of H goes to 0 as H tends to 0, and that error term we are writing as epsilon H times the UH, and that is estimated in this way. This comes from the definition of differentiability of f. See, from these two relations. Okay, and the derivative of f is given by a, and the derivative of g is given by b. From this consideration we get it. Now what we do is we want to work out the derivative of capital F, and we are expecting it to be dA. Okay. So given h, put k equal to f of x0 plus minus f of x. So we start with an h and corresponding k you take as f of x naught plus h minus f of x naught. Now you see, this is a vector in Rm, this is a vector in Rm, therefore k is a vector in Rm. H is a vector in Rm. That's where we start with. So k is a vector in Rm. Okay. So k is taken and this is well defined now. Okay. So k is such that, see, because f of x naught plus h is defined, f of x naught is defined, k is well determined. Now we estimate k. What is k? Norm of k, it is norm of this, is equal to norm of f of and this is essentially equal to norm of ah plus because you have it follows from the relation that a is differentiable at the point f is differentiable at the point x naught and the derivative is given by a. So what you have is f of x naught plus h minus f of x naught minus ah. This is what we have taken as uh and it comes from here. Okay. So this is this. Now you can estimate this. We estimate this as this is less than or equal to norm of a, norm of h plus norm of h, and that is further less than or equal to norm of a into norm of h plus epsilon h into norm of h. We use this. Okay. And one can write this as, put them together because h can be common factor. This is equal to norm of a plus epsilon h this is it, where all the norms are the right ones that you use or the appropriate norms are used, but although we represent by the same notation. Okay. So there is no need to be confused about it. So this estimate we have, so the estimate that we have is that norm of k is less than or equal to norm of a plus epsilon h times f. Just put it out here somewhere so that we can use them. We need to use them. Take out the whole thing. One has to be careful about the order in which you do things and so on. It's not that you can work as liberally or freely as we did in the case of the derivative of a real valued function, because we are now working with vector valued functions. So one has to be careful. So let us keep this for use somewhere here, that is the estimate. So we shall just put it in a box. Now here one should remember that k is given by f of x naught plus h minus f of x naught. Therefore, now let us start working on the derivative. So we estimate this, or we have f of BH is sensible. You see that this is in RK, this is also in RK, and BH, H is in Rn, and BA is a linear transformation from Rn to RK. Okay, and therefore all these terms belong to the same, are of the same class. Okay, so they are all in RK, and this is by definition G of minus G y naught minus this is it. And this you can write as use this b of y naught plus k minus g of y naught plus k minus g of y naught. Okay, g of y naught plus k is, so recall this is equal to b ct. So use that. So if you use that, then this is what you get. Therefore f of use this here. If you use that, then this is equal to b acting over k minus h plus pk. Therefore, go from here, we have norm of f of this is less than or equal to norm of this minus plus norm of this. Okay, so this is actually what this is equal to. So we have estimated this. What is that we have estimated? Sorry, I think I made a mistake when writing again. Go down this minus BH equal to B this is it. So we are estimating this. Therefore, this is equal to norm of B into B operating over K minus AH, or rather I think we can write it as VK this is what you get, and this is less than or equal to. Now we start replacing this. So we get this is norm of B into norm of K minus AH plus norm VK is, you write it as eta K into norm of K and this is less than or equal to norm of B into norm of K minus AH plus eta K. What we do is we have the estimate for K here, so we replace by that, this upper value of that or the bound for that, norm of A plus norm of H okay, so we write that. Therefore further now we estimate this. What is this? So we look at this f of, see, K minus AH equal to f of x naught plus minus f of x naught, that is part K, and minus AH, and that's equal to UH. Therefore we have, now you can use that norm of K minus AH will be then norm of UH. Norm of UH is what? It's epsilon H into norm of H. Okay, therefore norm of f of x naught plus h minus f of x naught minus BAH UH divided by norm H plus this part, that is norm of eta K This is it, because this norm h and norm h cancels there. So you get that. And this is, of course, equal to norm of B epsilon h, because norm of UH you can write less equal to epsilon h into norm of h, and h cancels. Okay, so this is there plus eta k. So after estimating that, now we can come to the conclusion that what we conclude is that this goes to 0. This goes to 0 as epsilon h goes to 0, or h goes to 0, epsilon h goes to 0. And from the definition of eta k, this also goes to 0. Right. So we write down that. So as look at the definition of k goes to 0, and that implies what is it? Epsilon h goes to 0 and eta k goes to 0. As h tends to 0. Okay, so use that. If you use that, then this follows that limit norm of BA that is that is f is differentiable at x naught, and f derivative at x naught dA, which is essentially g derivative at f of this completes the proof of the theorem. Okay, so that proves the theorem. So the result holds as it is, except for the caution that you have to exercise while writing things, because you know that in the higher dimensions the operators do not commute. That's the reason. When you take the product, one should be careful, because AB is not the same as BA. That's the difference. So one has to be careful about the order in which things appear. Okay. What we do next is, we talk about the directional derivatives, especially the derivatives along the coordinate axis, so that you get the so-called partial derivatives, and then connect the total derivative with the partial derivatives wherever it is possible. And I am very cautious that it's not always the case that if the partial derivatives exist, then the total derivative exists. That cannot be guaranteed. When you write down the partial derivatives, you are only talking about derivatives along certain specific directions. Because if you recall, if you have a function of several variables, something like, say, just a real valued function of n variables, say, so something like f of x1, x2, etc., xn is the function of n variables x1, x2, etc., xn. Then you talk about what are called partial derivatives. We have already seen it. What we do is we keep, say, if you are taking derivative with respect to the xj, then we keep all other derivatives, all other variables as constant, and then only vary xj. That's how we compute the derivative. So there are certain directional derivatives in some sense, okay, and such derivatives we are already familiar with. Now what we are trying to do is to connect the notion of derivative with the partial derivatives wherever one can connect them. Okay, so let us start with the necessary preliminaries. Want to make certain definitions. Partial derivatives. Let us fix a notation first. So let f be a map from E, which is assumed to be open Rn into Rn. We are talking about mappings from open set E to Rn. Let be the standard basis for Rn, and U1, U2, etc., Um be the standard basis for Rn. So we use these notations. I mean, not to get mixed up, we use different notations. Okay. And suppose you talk about the vector valued function. So let f be a map from Rn. Then it's a vector valued function. The components of f are real valued functions, and let f be equal to Fi. That is, f of x is equal to sigma ui. So this is what you mean by this. These are the components. Or fx dot ui equal to fi of x. This is the equivalent form for now let us define for x belonging to E, for 1 less than or equal to I less than or equal to n, one less than or equal to j less than or equal to m. Let me take it this way. Define djfi at x equal to limit t tends to 0 fi minus fi of x divided by, provided of course the limit exists. So that is the definition. This is what is called the partial derivative of fi with respect to xj. Okay. Now this we are familiar with. This is called the partial derivative of phi. This we denote by conventionally denoted by a partial derivative of fi j. So we'll write this as d this is it. Now for n equal to 1, in the one variable case, both the partial derivative, the total derivative becomes the derivative. The existence of derivative is sufficient. The is d total derivative. Because we are talking about real value differential. But for n greater than 1, this is not the case. The total derivative is different from the partial derivatives. These are all the directional derivatives. The partial derivatives are directional derivative derivatives and standard base vectors okay. Now what the problem that you encounter is that, see, lot of complexity enters when we deal with functions of several variables, and not only that, vector valued functions of several variables. We cannot say, for instance, the partial derivatives may exist, but the function is not necessarily differentiable in the sense in which we have introduced the derivative. This problem does not arise in the case of single variable and single value and single what you call the functions defined from E to R, where E is a subset of an open subset of R. So from R to R, if you are defining, and then when you talk about derivatives, it's a different story altogether. Okay. Now it is, even if these directional derivatives exist, now let us look at this problem in a way. See, suppose you have, this is R. Now suppose you are defining a function from here to R, a real value function. So this is the variables are, now you take a point x0, so you let us take x10 and x20 as the coordinates of this point. And you are talking about the partial derivatives here. Partial derivative means what? Suppose you are taking the derivative along the x1 direction, then you are taking the function and treating x2 as a, because this is a line. What is this line? This line is actually x2 equal to x2 equal to x20. So you are considering the whole problem along the line x2 equal to x20 then you see it's a real valued function of a real variable, and the only variable now is x1, and then you are talking about the derivative of that. Likewise, when you are talking about the derivative with respect to x2, then you are keeping x1 not fixed. That means you are considering only the line x1 equal to x1 naught constant function, and then working out the derivative. Okay, as it's a single valued function. So in short, what you are doing is this. Okay, let me write this for clarity. I think it may be much more clear if I use the notation. Suppose this is the point A1, A2. It's a fixed point. Okay. Now what we have is this line is x2 equal to A2. This line is x1 equal to A1. Now you see the point A1, A2 is the intersection of these two lines. Okay. Now what you look at is this. You are looking at the function f of x1, x2. You are keeping this. If you are interested in the derivative at this point, then what you are doing is you are look at this function f of x1, a2. Now you see this is a function of a single variable x1, and then you differentiate it with respect to x1. Similarly, you look at this function with x1 as a1, then you are working on this line. So the increments that we take only along this line. Okay. Therefore, you see the rate of change of the function is studied along this line and along this line. The partial derivatives give this information. Okay. Whereas the total derivative is something that you talk about the differentiability of the function at the point a1, a2. So which in a way means that irrespective of the path you take to approach the point a1, a2, the limit that we have written whenever the derivative exists gives you the same thing. Okay. So that's something that we have to be careful about. So it's an awful restriction that you have when you talk about the function is differentiable at the point a1, a2, and when you say the function is differentiable along the one axis and along the two axis passing through a1, a2. That's the reason. Okay. So you can expect lot of complications to arise in this case. Now what we will do is, we have already spent some time looking at several examples earlier. Some of them we may recall again, and we shall look at this and get a feel for these complexities. And essentially what we are up to is the following. The question that we are going to ask is this: how the total derivative is connected with the partial derivatives. Okay, the relation between the two. Okay, so this is what we are up to. So let us take up this problem in our next lecture. So I will first open with number of examples and then connect the partial derivatives and the total derivatives wherever they exist. Okay. Thank you very much.